So good morning, everyone. This is lecture number 28, E524 Digital MOS LSI Circuits, and today is October 15, 2020. Note that today is the last day to drop the course in case if you are feeling difficulty and if you think that you are not able to cope up with the given load. But I think one should not leave it if they don't have the plan B, right? So, and in case of any difficulty, you can write me, not a problem. I'll try to answer if it is possible, right? Okay, so we were talking about the pass transistor last time, and before pass transistor, we talked about various techniques like CMOS uh, technology, where PDN and PUN are there. By the way, these are coming under the static logic gates. So we are studying static logic gates. In CMOS, it's power up network and power down network, which is going to be there. Other than that, we have studied pseudo NMOS technique, where there is always a PMOS connected to gate with the ground, and there is a PDN, and there are various inputs are there, and you are taking the output from here. The only problem is you can't reach VOL to 0 volt. It's not rail to rail, not rail to rail. So that's the problem over here. But to deal with it, we found out that there are two things which are very useful. One is regenerative negative positive feedback, and the differential logic. So by use, so that has been done by the technique called DCVSL, which is differential cascade voltage switch logic, where you are keeping all the transistor in cascaded mode so that you can have the output rail to rail. Note that when we are having this DCVSL, you not only having the F as output, but you have F bar also as an output. So two outputs are available at a time. So that's the best part of this. Without having any propagation delay, you will have the output. So this is what we studied, but we are very greedy and we want to reduce the number of transistors. So we are using something called pass transistor logic. So till this DCVSL, we have learned that you can give input to the gate. So input was given to the gate only, right? So here in pass transistor, we are saying that not only give input to gate, but you can give input to gate as well as source or drain, wherever you want to give, so that you can have the output. So this is what we already learned, and we also learned that if we have such kind of possibility, like one more thing has not been shown over here, that when it's in bar, it's connected to ground. So this is the pass transfer logic. If you remember, like we did it so that this node should go to 0 also, otherwise it will not go to 0. Now if my input is VDD, means one of the input A is equal to VDD and B is another input, then what is going to happen? In that case, X node can reach up to VDD minus VTN only, because after this volt, I would say that, yeah, VDD minus VTN only, keeping into mind that this is also VDD. Okay, so you will always have some difference which is of VTN, right? So this is what the problem is. There is one more thing we need to understand. There are two possibilities. Like one is you can connect like this, and one you can connect like this. By looking at this by looking at this slide itself, you could have assumed that this is the wrong way of implementing it, because if there are two inputs A and B, X will be equal to VDD minus VTN, with the fact that this is VDD and this is also VDD. Now note that this is also VDD, then this node cannot go up to VDD minus VTN 2, but what is happening, because of gate voltage which is connected to VDD minus VTN 1 is referring to the first transistor's threshold voltage, and VTN2 is the referring to the threshold voltage of the second transistor. In that case, because of the gate input which is connected to VDD minus VTN1, you can have the maximum input of maximum output of VDD minus VTN1 minus VTN2. And after this, if you want to charge more, like your transistor is in off condition. So before inverter, sorry, at the Y. Whereas at the output, this will be like, considering the fact that this is logic high enough, then this will be connected to 0 at the output because of this inverter usage. So that is one of the technique. So we are saying that you should not what this golden bullet says, that the above example demonstrate that the pass transistor gates cannot cascade it by connecting the output of a pass gate to the gate input of another pass transistor. If you do that, then you will not have just one threshold voltage reduction, but you will have two threshold voltage reduction. If both of them are equal, then it's VT minus 2 VTN. That's the reduction in threshold voltage. So it's better that you go with everything is VDD over here, also VDD over here. If this is also VDD, at the Y you will have VDD minus VTN only, not 2 VTN. Maybe you can make a thought on it and you can understand what exactly is going on. Right. Now let's go to the next part. The next part is one circuit, which is a pass transistor, and it's an AND gate. Now there are two different possibilities. One possibility says that when B equal to 1, and means B equal to 1 forever, and A is rising from 0 to VDD. So if I am doing this, what is going to happen, for some times, like till the value of VTN, when the A input is around VTN, somewhere here, let's say, the most like transistor is not going to become transfer anything, because the output is VDD minus VTN. So most of the thing is going to be 0. You can't say anything. But progressively after VTN, this is going to start rising, and this is going to change the operation of working operation of the region. Then you can see that sharp transistor, and thereafter whatever the input I am giving, I can see the output, but with the difference of VTN. So with the difference of VTN, you can have the output, which is well evidenced, and this is visible over here. Okay, sorry, this is not the second output. Yeah, when A is equal to going from 0 to VDD. So this is what going to happen, and it is going to stop at the point where it's VDD minus VTN. Note that threshold voltage over here is actually 0.5 volt. So this is still 2.5, but this is threshold voltage of 500 millivolt. That's why it's getting stopped there, and that's following the equation VDD minus VTN. Okay, or you can say that in this case A minus VTN, whatever the A you are giving. So lower side it will transfer the strong logic 0. As it's going high side, it cannot transfer the whole logic, but it will be reduced by VTN. But if you are looking at the another condition where A equal to VDD, means this is connected to VDD, and B is going from 0 to VDD, B is going from 0 to VDD, then what is going to happen? First of all, of course, there will be some propagation delay, because of which this is going from VDD to 0. Look at this, right? It will not be exactly like this, but it will be something like this, right? Which is going to be given to B, B bar, and that will make this transistor on and off. So when it's 0, this B transistor is off, and it's waiting for the value which is 1.25, with the assuming that after that this particular transistor becomes on and this particular transistor becomes off. So in that case, when this is on, afterwards output here is going to follow the input, but with the it can reach up to VD minus VTN only, right? In the reverse way, when A and B both are going from 0 to VDD, then also it will follow the same thing, right? Because the lower part, which could have been transferred by this transistor very strongly, it's not able to do that because of it's able to do that because logic 0 is already available. But at that time, this particular transistor is not on. It's waiting till 1.25. So before 1.25, it's almost 0, and afterwards it takes a ramp up, and the input and output are equal. But when A is equal to VDD, the output is VDD minus VTN. So you cannot achieve the rail to rail output over here also. So there is another technique which is already known to us. So whenever you want to have the rail to rail or other things, you can use differential, or you can use the positive feedback, or you can make that as latch. So here, let's assume that positive feedback is the second part, but first part, let's take the differential input. If we are taking the differential input, what does it mean? If one side of the input is given with A, another side has to be given with A bar, right? Because they have to be phase shifted by 180 degree, or they have to be complementary to each other. And same for the output also. If output is F, output other side will be F bar. Notably, these networks might be changing, but the input side, the pattern has to be A and A bar. As told, that complementary pass transistor will use the differential structure. You can call this one as also differential pass transistor, DPL or DPT. Okay, its logic also is there. That's why it's known as CPL and DPL, right? The name is DPL and CPL. That's how it's popular. So logic, I forgot to write. So CPL stands for complementary pass transistor logic, and another one is differential pass transistor logic. Now, look at this structure where you can see if I am giving input as AB, other side will be A bar, B bar, right? And this is first circuit, and this is second circuit, right? The only problem here is the number of transistors will get double, but at the same time you will get two outputs, F and F bar. Similarly, you can make other circuit where again the inputs are A and B, other sides are A bar and B bar, and you will have F and F bar, which are making the OR and NOR gates together. Same way, like you can make the XOR and XNOR also. By the way, now I remember last time I made somewhere mistake. Yeah, last time I was saying that this is not XOR and not XNOR. I made mistake there. Actually, because of this, it's AB or A bar B bar, it's okay. So if you follow this, you will have XOR and XNOR. You can see the connection. I made the wrong connection at that time. So it's XOR and XNOR. You can analyze accordingly. So because of this XOR and XNOR, I just remember that you need to check that. Anyway, so this is also making XOR and XNOR, where if you are giving input as A and A bar, you can see the pattern of the input has been changed to be A bar and A. You are seeing the output F and F bar, right? So this way you can make the complementary pass logic, which is CPL. You can call it DPL also. Some books are following differential pass transistor logic. So that signifies that it's DPL, but both are synonym. Both are same technique. Now, the problem here is already we know that AND gate is like this, not differential one, not complementary. But here, if this is 0, and if this is VDD, I can transfer 0 over here. VDD is not going there. Still, the problem is for VDD. I'm not talking about the other part, but I'm talking about when A is equal to VDD, the output is VDD minus VTN, right? Where VTN is the threshold voltage of this transistor. What I can do, I can add one inverter. So then this VDD minus VTN will go to 0, and in another case when it's B bar, the 0 is already there, so it will be lifted to VDD. However, let's assume that there is one more technique which is known as the bleeder technique. What it says, I'm going to keep one PMOS transistor over here, and whose gate is connected to the output, and here this is connected to VDD. So now what is going to happen if the output of this one is VDD minus VTN? This will go to 0, digital logic 0, and this 0 will make this transistor on. So this transistor is on, and this particular potential is rise to VDD instead of VDD minus VTN, right? So now it's not VDD minus VTN, but it's VDD, and you can have the full swing at this node itself. You don't need to look at this output. However, this output was also fine, but this particular thing is going to be executed when this is VDD minus VTN and the output is 0. In case of output as VDD, this transistor is again it's off, and there is no role of this transistor. Okay, so that we need to understand that if this is 0, the output is VDD and this transistor is off, then this loop will not be there, or this is known as the bleeder transistor. Okay, now the problem here is, let's assume that there is a capacitor, parasitic capacitor, or you keep some capacitor over here to hold the charge. Now what is going to happen over here? If let's go to the first condition. If this is VDD and this is VDD, I am transferring VDD minus VTN, and because of the propagation delay in this loop, along with this capacitor, I am going to have VDD over here after some times, after some PMOS transistor multiplied by this capacitor. So node capacitor, let's assume that this node capacitor is the biggest one, right? And it's a combination of the capacitor by this one, capacitor by drain to body. This is gate to drain, and input side, that is Cox, the biggest capacitance Cox, and this side there is a capacitance CGD. So all these capacitance altogether is going to be reflected over here, and I'm calling them as a big capacitor C, and that capacitor will be definitely the biggest one, and they are coming from the individual capacitors, or you can keep the capacitor bigger than all these parasitics. So then you can find out what is the propagation delay at this node by the Elmore delay. Now it's not creating a problem, but let's call this one as Mn and let's call this one as Mr, right? So here, by making the W by L such a way that the Vm is equal to VDD by 2 and rise time, fall time are equal, or maybe TPHL or TPLH are equal. So that's not a problem. The problem here is we need to make sure that when we are doing this, this transistor is on, this transistor is also on, and because of that, when this is transferring here VDD, because of VDD minus VTN, on top of that, the VDD is going to write, and here it will be VDD. But what if I change to 0, right? So if it is 0, other side will go to 0, and other side is VDD, and this is going to be off. But this is the theoretical business. If you understand this thing, that 0 will take some time to reach over here, and after some, the whole loop and this particular propagation, after that this becomes 0. So it does not go to 0 instantaneously. It takes some time, and that time is depending on two factors. It's always like it's a RC time constant, right? If I want to transfer this VDD to here, it takes resistance offered by this PMOS multiplied by the capacitor, and when it's 0 is going here, it's a resistance offered by this one and multiplied by capacitor. But note that when I'm transferring this to 0, what I exactly mean to say, let's call this node as Vx. A was VDD, and then I'm making it 0. So this is A. Earlier it was VDD, and afterwards it goes to 0. And all the time VDD, B is equal to VDD, no problem. So let's say B is equal to VDD. And I'm looking at Vx node. So Vx is already known to me that it's actually equal to VDD minus VTN. And because of this propagation in this particular bleeder loop, this will go up and remain at VDD, right? Note that this particular transition is because of this propagation delay. But now this has reached VDD. Now I want to keep this Vx equal to 0. So when I'm doing this, note that still this transistor is on. This transistor is on. And I'm transferring instantaneously 0 over here. So that cannot be done because this transistor is also on, this transistor is also on. Means this node is actually trying to connect it by two things. One is by input A, which is connected to 0, and one which is connected to VDD. So this transistor push this node or ask this transistor to remain at VDD, and this particular input is asking this particular node to go to 0. So these two transistors are fighting until this is not going below minus 1.25 volt, below for the case of 2.5 volt of VDD, until this node is not going less than 1.25, this node is not going to become VDD, and this particular transistor will not become off. So until it's less than sorry, it's until it is more than 1.25, there is a fight between these transistors, because the resistance by this transistor and resistance by these transistors are playing the key role over here. So unlike the case of the inverter, when we were keeping the W by L of this transistor, MR transistor, if you remember, we used to do this one. That W by L of NMOS and PMOS have this relation, some number beta. Beta is actually the mobility, right? So PMOS transistor was always higher than NMOS transistor because of the lower mobility, and you are adjusting with the ratio of mobility of PMOS to NMOS. But here we don't do that, because if you will do that, this particular node will never reach to 0 volt. So if you know that electrical connection works such a way that wherever there is a low resistance path, that path will be given for the current, right? So in that case, there are two particular paths are there. One is for Mn and one is for Mr. So in both cases, the resistance will be offered. So which resistance has to be higher? You need to have R on resistance of R has to be much higher than R on resistance of PMOS, sorry, of NMOS. If I want to reduce this, I know that as I am going to increase W, resistance is going to get decrease. So W is increasing, resistance is decreasing. So in that case, W by L of NMOS has to be much higher than W by L of this MR transistor, so that things will be properly working. So this needs to be understood. Otherwise, this will be remain at VDD or maybe some potential which is less than or maybe much above VDD by 2 and qualify as a digital logic 1, but you wanted to make this one as digital logic 0. So you need to make that particular transistor stronger. When I'm saying stronger means resistance is smaller and it gives the path. So I need to make this transistor stronger rather than this one. Okay. So that is what all about for this technique where you are not getting the rail to rail output. So this technique is also known as level restorer. It restores the level to VDD, and again other side 0 is not a problem, right? But 0 is problem in the presence of this loop. In that case, you need to make sure that W by L of R transistor has to be much higher than, sorry, much lower than W by L of N transistor, right? Now, as we know that there are certain problem over here. If you are not using this one, there is a problem. Problem remains because let's assume that just that much part we have. We don't have the whole loop. If we have that much loop only, in that case, if B equal to VDD, if A is changing to VDD and 0, no problem. It will be transferred over here with the correct value of W by L. Things will be fine. But what if it is 0? If it is 0, I'm expecting here the output to be 0, because this is an AND gate where any one of the input is 0, output has to be 0. To get the VDD as output, both the inputs has to be 1 1. But in the case of B equal to 0, look, this particular node is not going to get discharged to 0. Note that because of this B equal to 0, we want this one as 0. But here what is going to happen? This particular transistor is going to get detached. It's open circuit, and whatever the voltage was here, held at the positive plate of the capacitor, it will remain there. It will not go anywhere, right? There is no discharge path, right? I don't see any discharge path because input of this one is infinite, input of this one is infinite. Some sort of looking at this drain, that is also R0, so that is also infinite, or you can say bigger value. So there is no path where this whole charge capacitor goes to 0. So in that case, it remains at the value where it was. So if this node is connected to VDD, like just before this one with the level restorer, if A was VDD and B was VDD, and then I change this to 0, this node will remain at VDD forever, like in the ideal case. So in that case, you don't need only this loop, you need this loop also. You need to make sure that for the B bar, 0 has to be there. If it is not there, you can't tackle with the condition when B equal to 0, right? So you can't achieve this. Of course, you can achieve this one if right before making this B equal to 0 from B equal to 1, if this is A equal to 0, then that output will be correct. But this is not true for all conditions. So I suggest either you keep this one, or to take this output to other side, what we need to do, we need to make the differential structure or make the latch as follows, which is already known to us. We can use two NOT gate back to back like this. By the way, this is known as the regenerative positive feedback, or it's also latch circuit. This will make sure that this node, let's say if it is X and this node is Y, X is always equal to Y bar, right? Or they are non-overlapping one. You know the meaning of non-overlapping one means when X equal to 0, Y equal to 1, and when Y equal to 0, X equal to 1. And when both are actually midpoint, both are at midpoint, right? So generally this is what happened. For that, careful W by L of NMOS and PMOS of both the transistor has to be done, which you already know how to do that. So here at the bottom side, you will have something called PDN, power down network. But as it is a differential one, you are going to have two outputs, both are like complementary to each other. And when you are looking at the input pattern, one side F and one side F bar is going to be given. So look at this particular node. So this particular node has, right? So this red connection connects to O out. So in that case, what is out is equal to nothing but, you can see here, B bar ending with, sorry, B bar ending with C bar and ORing with C or, okay, I forgot to take this A also. So first of all, this becomes A, B bar, C bar, right, which is here. In this case, it's in parallel connection, so it's OR C times AB or A bar B bar. Note that everything has to be complemented. The reason is output is connected to, okay, sorry, no, here it's not complemented because of the fact that it's not connected to 1 digital logic 0. So this will be the out, this will not be there, right? And similarly, you can have the out bar, which is actually complement to the same thing, and you can find out from here with the fact that it makes the connection right? So it makes the connection as follows. So yellow part is out bar, and you can write down that also, which is very simple, like a b bar or a bar b, and with c, and oring with a bar, b bar, and c bar. So that will be the out bar. It will be making the complement of this one only. Now there is solution number 2, which says that if you just, for quick recovery, there are two kind of transistors. One is called enhancement mode, and one is called depleted mode, or the depletion mode. This is also known as zero VT device. So in enhancement mode is the one which you are studying, the normal one. So whatever you have studied till now, whatever the symbols you are seeing, all are enhancement mode. One is called depleted mode, which has channel is always there. Just the input has to be more than 0 volt, more than 0 volt, and this transistor is on, right? So that is called zero V2 device. Also means if you are more than 0 volt, the transistor is on. Lesser than 0 volt, it's off. So there are two things like a relay. So that's why these are useful where there is no drop at all. Like earlier we were seeing that if this is the case, A equal to VDD, B equal to VDD. Here you used to see VDD minus VTN. But if this transistor is not a normal enhancement mode, but if it is with this dark, uh, dark area just below the gate, it's known as the channel length. Channel is always inverted, and you need just more than 0 volt or the low VT device. So in that case, this VT will not be there. There is no drop at all. So the output is VDD because the VT is 0. So that kind of transistors can be used to implement the CPL logic as well as the pass transistor logic, so that there is no voltage drop. But you need to use these special transistors, like we are using NMOS 4, right? Then PMOS 4. There are availability of NMOS also and PMOS. In case of NMOS and PMOS, these are the 3-terminal devices where body is not connected anywhere, right? These are the 4-terminal. So similar to that, there must be some zero VT devices that has to be taken. I don't know whether they are available in Simica or not, but if they are not, like in real Cadence, the design kit, you will have this zero VT devices, right? You need to read that which transistor is zero VT device. For that, the information will be given in DRM or design rule manual. Now, the third rule says that, which is also one of the intelligent way and the most popular, which is known as the transmission gate. Some people call it TG. What it does, not keeping only one transistor like NMOS or one transistor PMOS as a switch, but we are going to keep both of them in parallel. But before that, let's understand one fact that we learned in previous few lectures, that if I want to transfer zero logic or ground other side, then NMOS is very good. Means if this is connected to VDD, if I am taking this NMOS, other side is 0. But if I am doing this with VDD is here, output is VDD minus VTN, and same thing is happening with PMOS. If this is connected to VDD, output is VDD, but in the case of ground, output is not ground, but it's little bit higher than that, right? So it's VTP, right? So it's not transferring good logic. Means NMOS is good for strong zero logic transfer, and this is good for strong logic 1, right? So wherever you know that if there is any connection, like there is a switch where you are making a connection, other side is 0, you know that I'm going to use always NMOS over here. But if it is not like that, if it is connected to VDD, I'm going to use that one as PMOS. But when both are there, or you don't know that whether it will be VDD or ground, and it will be changing from VDD to ground, you can use the characteristic of NMOS and PMOS both together, and you can use something called transmission gate. What it does, it says that keep both of them in parallel. Let's assume that this is 0 volt, this is connected to VDD. So here, whatever the input you are connecting, let's call it A, and this one is A bar. So if A equal to VDD, what is going to happen? This is going to make the connection. This is going to make the connection. Similarly, this becomes 0, so this will also make the connection. Both are in parallel. So 0 will be transferred to that side strongly, because this NMOS has a characteristic that without any voltage drop, you will have the 0. But if you change this one to VDD, because of the characteristic of PMOS, this will be transferring the complete VDD without making any voltage drop. So this combination is known as the transmission gate, where NMOS and PMOS both are in parallel. Notably, it has a symbol like this. So this is input, this is output. Here, whatever you are connecting here, let's say I'm connecting here A input, then it has to be A bar. If I'm connecting here clock, whose symbol is 5, I can make 5 bar also other side. So it has to be complementary only. Then and then this will work efficiently, otherwise no. So this is the symbolic representation, and this is the circuit. In circuit, both the transistors are in parallel. Now, as I explain you, so if there is a transmission gate where A is equal to VDD and the node B initially at 0 volt, and capacitor is either you are connecting physical capacitor, or you might have the capacitance created by NMOS and PMOS, means the self-loaded capacitor. In that case, if A is equal to VDD, C equal to VDD, this particular node should charge to VDD, or should go to VDD with the propagation delay coming from the resistance both in parallel. So it will make RON N in shunt with RON P. So whatever will be the resistance, that resistance will allow this this VDD voltage to go to the node number B. So in that case, when it's transferring, it goes there and it's go to VDD, because of the fact that this PMOS is also there, which has the characteristic to transfer the whole VDD. So till the time VDD minus VTN, this NMOS is on and it transfer the logic, but afterwards this becomes off, as you know that, right? But afterwards still this transistor is on, so this particular path will allow this VDD to transfer from point number A to point number B, and it will take further. And same thing will happen when it's going from VDD to ground. Till VTP, this PMOS will act properly, but afterwards this NMOS will take care of this particular logic to go to 0 by its own characteristic of sending strong 0 at the other side. So that is what we are doing, and we are getting the rail to rail swing. So all the implementation of CPL means complementary pass transistor or pass transistor logic, you can use such kind of transmission gate so that you can have the output as you want. Now let's okay, so there is something called MUX, 2:1 MUX I want to implement. MUX is, by the way, multiplexer. I call it in a short form, so everyone call it MUX. It's a multiplexer. It's a switch, by the way, right? You must be knowing that 2:1 MUX works as follows. there are two inputs, I0 and I1, with one output. So this 2:1 indicates two inputs, one output, and you will have 2:0 numbers of selection line. So here generally 2 raised to n cross 1, that's the multiplexer we have, where n indicates the number of like lines coming to the input side. So here it's only 2 raised to 0, sorry, 2 raised to 1. So only one selection line will be there. Sorry, n selection line rather than this. So this will become one selection line. And what this one selection line does, if at this selection line s equal to 0, I0 will be available at the output. If s equal to 0, output is equal to I0. If s equal to 1, output is equal to I1. This is what I want. So whatever is available, I can do that. Sometimes like in interview, and you must have learned it in your basic course of digital electronics, where you might be interested in making two input AND gate using 2:1 mux. In that case, what I can do, I know that when, so there are two things, A and B. So I know that when the selection line is 0, whatever is available here, it will go to the output side. Means if B equal to 0, I'm keeping here B. If B equal to 0, whatever is here, that will transfer over here. But at that time, I want to transfer 0 only. So I can connect this one to ground. When B equal to 1, then I1 will be selected. So if I connect this one to A, whatever A will be there, that will be transferred over here. So if A equal to 0, so 0 times 1, it has to be 1. If it is 1, 1, 1, both has to be 1. So all four all four possibilities has been taken into account, right? So, and if it is like other also, like all four are there. So this is what I want to do, and this is the answer for 2:1 mux based AND gate. So now I want to implement that in our circuit. So what it does, I'm making sure that when selection is 0, this point has to be equal to A, and when selection bar is 1, I want B over here, and then inverter is there, so it's a different thing. So in that case, what is happening when s equal to 0, right? So when s equal to 0, this is off, this is also off. So at that time, B is selected over here. So sorry, it's reverse one. When s equal to 0, B is the output, and when s equal to 1, you can keep the other one. You will see that s equal to 1, this is selected, no problem, and this particular transistor is going to be off. So A will be here, or A will be transmitted over here without any losing the supply voltage in terms of it will not be VDD minus VTN, but the output is VDD in full value, and after that inverter you can drive whatever you want to drive. Okay. Other than that, transmission gate, like you can do following things, that if there is an inverter, just after this circuit will sign off. So if there is an inverter and other side is transmission gate, right? So here B bar and B. So if B is equal to VDD, what is going to happen? This is connected to VDD, this is connected to ground, right? And this is the output, by the way, F, and this is becoming off, this transistor also becomes off. So F equal to A bar when B equal to VDD, right? That is what being happen over here because of these two transistors off. Now, when B equal to 0, what is going to happen? This is going to be look like this one. Look at this, the position of NMOS and PMOS both are changed. Now here, this is connected to, right? And this is connected to, right? So this is what happening when B equal to 0, B bar becomes VDD. So this is A and this is F, by the way. When you are doing this at the same time, both the transistors are again on, and whatever A is here, that will go that side, right? And here the output is. So here both the branches are there. Note that this is known as buffer also, because input and output are equal in this case. Just forget about this part. In this part, F equal to A, but the only problem here is when A is equal to VDD, F is connected to VDD, but because of this NMOS on top side, the output is not going till VDD, but it's going till VDD minus VTN. Other side, it's VTP only. So the output will be either VTP or VD minus VTN. But thankfully, we have another also connection where the full strength of A will be transferred over here because of the transmission gate. So it will override the remaining voltage, right? So that is what going to happen over here, and that's the XOR gate. XOR gate, what it does, you can, if you read the truth table, which says that. So look at the table where B equal to 1. When B equal to 1, the output becomes, this becomes 1 and this becomes 0. So that is equal to A bar. Look at this. Whatever the A bar is there, that will be there. In the case of reverse case, the output is actually 0 and 1, or it's A. So that is what done over here in the XOR gate, and that's how that XOR gate has been implemented. Just for the completion, you can see that when the resistance offered by both the shunt connection of Rn and Rp, and it will be much lower than Rp and like parallel connection of the resistance. So that is what is there. It's advantageous in terms of better propagation delay because the resistance is getting decreased for a given capacitor. But there is also one fact that the capacitor is also increasing. So you have to make the trade-off, and you should know that there is some input capacitance which is much higher than the capacitance offered by transmission gate. Then you will have always a positive impact because of the resistance, lower value of the resistance, and that is what happening here, because we are going to cascade the stages and chain of the transmission gates, and you can have always R equivalency, and all R equivalent is nothing but Rn in shunt with Rp, where Rn and Rp are the value of resistances when they are in a linear mode and offered by NMOS and PMOS in shunt. Okay, so that's all for today. Maybe we can talk maybe further more tomorrow 10 to 11. Okay, please let me know if you have any doubt on this.